Before the workshop starts, we're going to show you how to navigate through the video. Below the YouTube video is the Show More button. Click the Show More button to reveal the index. You can skip to the point that you want in the video by clicking the blue time link.
Okay, so you can see that I've left you out some unifix cubes then in between two people in your pairs. And what I'd like you to do is, could you do row F now? Okay, so put this distribution together, and what I'll get you to do is to answer these questions from distribution F. So have a wee look at what's the max, the min, the median, the mean. Well, you'll be doing that in order to get your moves, okay? So you're going to do F for me now together. Okay, so off you go then. Get stuck in.
Oh, sorry.
So we take a little bit of feedback then. So you were looking at distribution F, and when you ordered it out, you were able to tell a few things. So first thing you could find was the maximum. So what was your max then? 8. Perfect. What was your minimum amount of sweets? 1. Okay. So would you say, what would you say about the variation there? It's quite big. Yeah, it's quite a big bit of variation just there. Okay, the next thing then is the median. So what was your middle distribution, middle number? 7. Perfect. Okay, and then we know that the mean is 5. What do you notice about the median and the mean here? Yeah, they're different. They're different. So that tells me I have some variation as well, doesn't it? So this is flagging a bit of variation for me. This is flagging variation for me. So how many moves did it take? 11. So we're right, because 11 is quite a lot of moves, isn't it, to make it fair, compared to we had a distribution that had only 2 moves. So there's quite a lot of variation here, and we see that the numbers tell us that story. That's perfect. So what we're going to do then is, all of the answers and everything are online for you guys, so you can use all of those. We're going to now move from, we're looking at the moves here to tell me the story of the variation. But instead now we're going to move it into a more sophisticated way of measuring variation, which is standard deviation. That's what we generally use, isn't it? We wouldn't talk about the moves, we would just talk about standard deviation. But aren't the moves a lovely stepping stone into it, to talk about that idea of variability? Okay. So if I look at this, here I've got a dot plot, and it's a dot plot of one of my distributions. Okay, so it looks a little bit different to what you have in front of you. It's actually a dot plot of this distribution, this one here, okay? And what I can see is I've got 1, 1, some kid got 3, some kid got 4, 3 kids got 5, okay? 2 kids got 7, and 1 child got 8 sweets. So if I want to make a dot plot of this representation, I would say 1 person got 1, nobody got 2, sure they didn't? 1 person got 3, 1 person got 4. 3 people got 5. So that's going to be 3 dots, isn't it? Okay. Nobody got 6. 2 people got 7. And 1 person got 8. And now can't you see your dot plot there? Isn't that lovely? Because don't they forget that it's groups of 7 in their dot plot. So there you can just with one action show them how to change that into a dot plot. Okay. And it's the dot plot that we're going to look at then when we're talking about the standard deviation. Okay. The thing that we look at is, instead of the moves, we look at how far my data is from the middle, isn't it? From the mean. Now, what did we know about our distributions? The mean was 5. So we're checking out how far are these different data points away from 5. So this one here, can you see that it's 4 jumps less than 5? So I guess the deviation from the mean there is -4 for this guy. The deviation away from the mean here for this grouping of 3 is going to be 2, okay? And then the deviation from the mean of 5 for this one is going to be -1. Okay, these ones of 7, these data points that represent groups of 7, they deviate away 2 jumps in the other direction, isn't it? They're 2 bigger, so that's a +2 for that deviation. And this grouping of 8 is a +3 for that deviation. Now, standard deviation, it's so easy. All it is we're just going to get the average of all of those deviations. That's all it is. What are my deviations? Get the average of them. That's all our standard deviation is. Now, if I wanted to get the average, what am I going to do? What do I do here? Just add them all together and divide by 9. Exactly. Now, what's going to happen though when I add these the way they are? Yeah, exactly. They're all going to cancel out, aren't they? All these pluses and minuses are going to cancel out. So no good. So what do we do then to get rid of all of the minuses? We square everything. Okay, so we square everything so that we can get the average. Okay, so square everything. Then looking at these three didn't deviate any from the mean. So there's my 3 zeros. So we add all of these numbers up and divide by 9. Okay, and that's where we get our formula from for standard deviation. Okay, so we know that the sigma just tells me to add, isn't that it? Sigma just means add. This bit here is this is my mean, so take your data and how far away from the mean is it. There's my deviations. We squared them so we could add them. And then we divide by the number of numbers to get the average. And then, well, we sort of squared for our own convenience, didn't we? So what will we have to do with the answer? We'll just take the square root. Okay. So that's their standard deviation. And what's nice about that now is that they're able to use their calculator to get the standard deviation now. Okay? Standard deviation now is far more about understanding that it's a measure of variability rather than I can put all my numbers in a table and get out an answer and not really understand what it's about. So now the emphasis on understanding it's a measure of variability, and because that's the way it is, they're allowed to do it on their calculator and get their answer from there. Okay. So what we'll do is we better look at how to do this on the calculator. Again, all of this is online, so you'll be able to use these in your classroom. So we'll start with the Casio calculator. And what we'll do is we'll get the standard deviation of these. This was distribution A. Okay. So the very first thing, do you want to follow along then with this because it's long? So maybe get a calculator there between two, or just make sure you can see into one anyway. Right. So the first thing that we need to do is we need to put the calculator in stats mode, isn't that it? So go into mode and select 2 first, stats mode. That's always what we have to do first before we do any statistics. When we do that, our calculator will ask us, are you dealing in 1 variable or are you dealing in 2? Do you see 2 is a plus bx? A plus bx we know is a line, and a line is made up of pairs. Yeah, an x and a y. So that's what tells me it's 2 variables. All the rest we don't need to worry about. So our kids will only ever be concerned with 1 and 2. Am I doing single variable or double variables? What am I doing this time? Single, exactly. So we better tell the calculator number 1. Okay, so when we tell it number 1, single digits, it will bring up a little table and ask me for what is your data. And how you enter it in there is you put in the 6 and you press equals and it'll pop into your table. Okay, so 6 equals pops in, 5 equals pops in, and repeat the process then until you have all the way down to your 9 pieces of data in. Okay, so I'll give you a second to do that. And again, same as this morning, we'll do it for sharp after this. Make sure we know both calculators. When you've the data in, you have to AC back out of the data, which seems a bit weird. It's like you're letting it go. But what you've done is you've put it in, it knows what the data is, and you have to come back out before you tell it what you want it to do with its data. Now here is the difficulty that you might have in your class, because I know someone always comes in with a sharp when you've told them all to get Casio, and someone always comes in with a Casio, you told them all to get sharp. It's different with the sharp. The sharp people do not need to AC back out. So only the Casio calculators need to AC back out. So we'll AC back out after that. And what we need to do now is we go into our menu of stats to see what it is I want from this data. So do you see it's over the 1? So when you go into, it's a yellow one, so it'll have to be Shift 1, and your menu for your statistics will come up. So Shift 1, and there's your menu for your statistics. Okay. Now, I'm not a big fan of instructing anybody to press 1, press 5, press 3. It means nothing. They'll never remember it. So better to understand what they're looking for. Standard deviation, we now know, is a measure of variability, isn't that it? Or variation. So what we're looking for is VAR, which stands for variation. So that's what the kids have to choose. Forget that it's number 4, they'll figure that out. Choose your variation option. Okay, so we'll do that. And when we go in there, we see that one of my options is my standard deviation. Okay. And they would need to know to choose this sign for standard deviation, not the S of X, this one. Okay. And press equals, and your standard deviation will come up. So this is now the number that tells me about the deviation, or the variability. And if you remember, you did, what you put in there was distribution A. And remember, it had hardly any variability. So you can see it's quite a small number. Okay. Is everybody okay with that so far? Right, so if anyone has got sharp, or kids that come in with sharp, or etc. Sharp is a little bit different. Why it's different is you always have to clear the memory on a sharp calculator. Casio, it'll just overwrite. When you put in a new data set, it'll overwrite the old one. In sharp, you need to clear it, or it'll just continue the old data set and just make it bigger. So for the kids on sharp, they need to every time clear it. So here it is. Can you see it over the alpha there? There's the clear. It's red, so it'll be second function, alpha, and that will clear it for us. It'll ask us, what exactly do you want to clear? Just tell it number 2, reset everything. Okay? So number 2, reset everything, and it'll ask you to press a 0. It always does. When you reset your memory, it'll ask you to press 0. Press 0, and now we're starting from a fresh table. So the same as the Casio, we need to put it into stats mode. So we need to click onto our mode button and choose number 1 for stats. And the same as your Casio, what will come up is, tell me, are you using a single digit or 2 digits? Okay, so in the Casio it said 1 variable, in Sharp it just says SD, which I assume means single digit. Okay, or number 2, is it aligned with your 2 pieces of variable? 2 variables. So we'll choose 0 this time, single digit. Okay. So you can see that the Sharp calculator doesn't give a table. It's a different setup. What we need to do is we put in the data by using this button here. Do you see it says data? So every time you press that button, it nominates what you've put in as a set of data, as a piece of data. And you see the way it's a second function? You don't need to worry about that. If you're in stats mode, it knows that that button is the data button. Okay? So we're going to put in 6 and press this button, and it tells me that, look, I have 1, I'll go back there, in my data set now, you've put in 6 as a piece of data, in my data set I have 1 piece of data. Okay, we put in 5, and you can see when we put in 5, I now have 2 pieces of data in my set, and so on, all the way up to 9. Okay. Now, as I said a minute ago, we do not need to AC back out of this on the Sharp. On the Sharp, you just leave it as is and go straight in and get your statistics. And they don't have a statistics menu on the Sharp as such. The menu is all here. Their statistics are all second functions. Can you see that? They're all second functions. Now, if I look here, can you see here is my standard deviation? Just here, it's over the 6. So what I'm going to have to do now is it's green, so I'm going to have to press alpha 6. Okay, so alpha 6 equals, and there's my standard deviation. Okay. So there's the 2 of them, so that'll keep you covered now with all the kids, and helpful to go through it in class with them, that little PowerPoint as well. Okay. So is everybody comfortable with the calculator? Do you want to practice one, or are you happy to move on? Yeah? Okay. Perfect. And you can get the kids to do all of those. When they're finished doing all of that, they'll know how to use the calculator. It's enough practice for them. Okay. So as I said to you this morning, how we talk about data was we need to talk about the central tendencies, mean, median, mode. We need to say something about the variability of the distribution. So the max, the min, the interquartile range, and the standard deviation. And then the third thing that a student could look for when they're talking about the distribution is the shape. So the third thing that we're just going to look at now is the shape of the distribution. So here's a shape which we would say is symmetrical. Okay, can you see the left-hand side is the same as the right-hand side? It's symmetrical. So in a situation like this where it's symmetrical, we call it bell-shaped. Okay, so my distribution is bell-shaped. Now, in order for something to be bell-shaped, the mean and the median must be the exact same number. Okay, so the mean and the median here are both 25, which tells me that my data is symmetrical, which tells me that it's bell-shaped. So can you remember now, we had some distributions where our mean and median were the same. So now we know that they were bell-shaped, whereas we had some that weren't the same. Okay. Now, here's another sample, another dot plot. This is the ages of a sample of 300 students attending UCD. Okay. Who are these people? Yeah, mature students. Perfect. So what we say is, doesn't that distribution have like a tail on it? Okay. And because it has like a tail on it, we call this a skewed distribution. Okay. So do you know which way is this skewed? Yeah, it's skewed right. This distribution is skewed right. Okay. Now what's interesting is that when a distribution is skewed, this is when the mean and the median get separated out. Okay. Now, which do you think is going to be more affected by this tail of data? Is it going to be the mean, which will be the average age, or is it going to be the median, which is the middle person in this distribution? Which do you think is going to be most affected by this tail of people? Which do you think? It's hard, isn't it? Really hard. So what I think is, let's take the median. Okay, so we say we've our middle person somewhere here. Okay. Let's say I had a magic wand and I made all of these people a little bit younger, cha-ching, right? And so all of these dots come in here. Okay. Has my middle person changed? No. Can you see that? These people, if they're out here or they're over here, the middle person's still going to be in the middle. What's going to happen my average age if I make all of these older people younger? Yeah, it's going to get smaller. So actually what's affected more is the mean. What's affected more is the mean. And what happens is the mean gets pulled to the right of the median. So this tail pulls the mean to the right of the median. Okay. So that's a nice example, isn't it? So pull to the right. So, not really meant to talk about exam papers, but we will anyway, just because I like this question, right? Very simple question, honours leaving cert question. Here we've got a distribution. We've been told we've A, B and C. One of them's the mean, one's the mode and one's the median. So which one's which? Perfect. So A is the mode. Perfect. So it's the most frequent. And what did you say the mean was? C. Perfect. So the mean is C. It's been pulled to the right of the median B. Perfect. Okay. So again then we can have skewed left, and where the mean will be pulled to the left of the median. Now it could be just me, but I find it hard to remember which one's skewed left and which one's skewed right, because when I look at it I go, is it the tail that goes right or is it the big hump that goes right? Which one is skewed right, which one's skewed left? So I found this on the internet and I thought it was lovely. You might laugh, but it helps me. So your right foot is always skewed right and your left foot, your toes are always skewed left. Is that a nice way to remember? If you're like, which one is it? Skewed right. You should look at it if it helps them remember. Okay? Okay, so at this point then, we've done all of our summary, how we would summarize one variable of data. We looked at our central tendencies, mean, median and mode. And we said the median is best served in a 5-number summary with some context. We looked at the dispersion or the spread or the variability of the distribution by looking at the range, the interquartile range and the standard deviation. And now with shape, We have lots of different words describing shape. We can talk about, remember this morning we just said, oh, it's kind of clustered there. You can talk about it informally, or you can talk about symmetric, bell-shaped, it's skewed, it's normal. So those type of words then for shape. Okay, so what I'm going to do now is, we're going to go on and we're going to discuss shape a little bit more. Okay. Okay, so on your sheets, we're back to our census at school. Do you remember there was a question about foot lengths this morning? Okay, so there is 200 pieces of data on page 9 in your booklet. Okay. All right, page 9, that's it. Now, can you see underneath your data on page 9, you have your 200 pieces there, but underneath you've been told what the mean is and what the standard deviation is. Can you see that? Okay, let me get it out there. Right, so our 200 pieces of data, we've been told the mean and we've been told the standard deviation. So I reckon if we knew what the median was and the 5-number summary, we might be able to tell a lot about that distribution without even drawing it. Just looking at the numbers, we might be able to gauge what's going on. So what I'm going to ask you to do is to do a 5-number summary on that data in your pairs.
First quartile.
Right, so again, as said to you this morning, it's a lovely thing to ask, isn't it? And it's a lovely thing if a student's stuck and they don't know what to do with some data. Well, it's a great place to start to get their 5-number summary. So, what was the max then? 35.2, perfect. What was the min? 12. What was the median?
24.5.
Yes, exactly. 24 point, and as the 100 was 24.5, the 101st was 24.9. So the one in the middle, the average of the two in the middle is 24.7 because we had an even amount of data with the 200. So what was your first quartile then? Sorry? 22. And the third quartile? 27. Okay. Now, we had the mean already, didn't we? So look at your numbers and can you tell me anything about your distribution by looking at your numbers? The mean and median are very close. So it's exactly, there's a potential here for this being bell-shaped. We'll look at the other ones to confirm it though. We'll make sure, does my interquartile range, does it lie roughly in the middle of my range? Do your numbers look symmetrical? Let's just check it before we commit to the bell-shaped. Perfect. So your median looks like it's halfway between these two. So that's a lot of evidence for us, isn't it? That this is going to look bell-shaped if we draw a picture. Okay. I wonder now, does the interquartile range tell me anything? So let's just put it in. What is it? 22 and 27. So my interquartile range is 5. Roughly how long is our range? Okay, so we'll say roughly 23. Okay. So my range is 23, and my interquartile range is 5. Exactly, exactly. It's quite small. So this is small compared to the range. Perfect. So your data is much more close together. Perfect. Because what percentage of your data lies in the interquartile range? 50%. 50% of your data lies in this tiny range compared to this bigger range. So you're quite right. It's telling me that not only is it bell-shaped, it's one of those bells, isn't it? That's like this. Isn't it amazing how much you can tell from just the numbers? So what we'll do is we would get them in class then to do a wee chart of this. Now, what type of data is this? It's numeric, but what type? Continuous. Perfect. So what representation could I use for this? Yeah, a histogram would be lovely. A histogram would be lovely for this. So I have yes, it's over here. In true Blue Peter style, we've one made already, isn't that right? Right, we let the kids do it, but we'll move on. Okay. So isn't that mad? Isn't that what you expected from the numbers? Yeah, very good. So that's what we expected from the numbers. Now, this is actually, not only is it bell-shaped, it's something else because it's continuous data. Okay? The fact that it's continuous data makes it quite unique. So not only could I say it's bell-shaped, I can say it's a normal distribution because it's continuous. So the definition of a normal distribution is a symmetric, unimodal, just means there's only one point that's high, bell-shaped distribution of continuous random data, and that's called a normal distribution. So it's the very same as bell-shaped, isn't it? Except it's on continuous data. And it's very, very common in statistics, the normal distribution, okay? And it's so important. That's why it's on the course. It's so important. And what you find is the normal distribution, it's everywhere around us. If you think of the heights of the kids in the country, let's say we take all 15-year-olds in the country, okay? And we say the average height of a 15-year-old, we'll say boy. The average height of a 15-year-old boy is 5'7". Well, what we will see is we expect that to be normally distributed. All that means is we expect most people to be in and around the average height, with a few people that are exceptionally tall and a few people that are exceptionally small. So you see this in lots of situations. Most people are around the average, some people exceptionally tall, some people exceptionally small. Okay. And what would happen then is, if we took the right foot lengths there, but we only took it of 200 people, if we took the right foot lengths of every 15-year-old boy in Ireland, our distribution would have looked a lot more like this. It would have started to become more and more normal because we would have had a much bigger sample. Okay. So I think it's hard to reconcile, well, what do you mean it's just always going to happen, this normal distribution? Okay, how can you say that? There's a lovely machine called the Galton Machine, and I just want you to have a wee look at this. I'll turn off the light for you now and let you have a look at this. So I got this on our friend Wikipedia, very reliable source, but I loved it because it just explains what's going on here. Do you remember it says that the ball comes down and it hits the pin, doesn't it? And it has a 50-50 chance of going left or right on the pin. Now, in probability, What model do we use for things that have a 50-50 chance, or a success or failure where there's two outcomes? Exactly, the binomial, isn't it? Isn't that a binomial distribution where you have success or failure, or in this case, if you go left or right, and the probability of going left is 0.5, the probability going right is 0.5. So actually, the normal distribution is an approximate to the binomial distribution as well, which I think is really interesting. Because if you think about your binomial distribution, let's just say a plus b to the power of n. Can't we teach the kids to use Pascal's triangle as an aid for multiplying this out? Okay, so our Pascal's triangle is 1, 1, 1, 1, 2, 1, which we know are the coefficients if this is to the power of 2, or 1, 3, 3, 1, which are the coefficients if this is to the power of 3, or 1, 4, 6, 4, 1, if this coefficient is to the power of 4, and so on. But do you notice anything about those coefficients? It's the normal distribution, exactly. Look, the little ball comes down. It's much more likely to follow the path of the bigger numbers on the way down, whereas there's less probability of it going along the extreme values. These are the people that are either really, really small or really, really tall. Okay, the extreme people in a normal distribution. So I love the way it all matches up when you see that. It's very nice. Okay, so that's our normal distribution. And there's a lot that can be done with the normal distribution because of just how predictable it is. Okay, so we'll look at it a little bit more. Now, on your workbooks there, did you see underneath your set of 200 right foot lengths, you were asked about the standard deviations? Okay, so we were told in this case that our mean was 24.6 and our standard deviation was 4.06, and we are allowed to approximate to 4. So we're approximating our standard deviation to 4. Now what we're going to do is, and you would get the kids to do this, to look at the different intervals of certain standard deviations away from the mean. So here's my mean, 24.6. So one standard deviation away from the mean is plus 4, 28.6. So what will one standard deviation below the mean be? Perfect, 20.6. Then we'll look at two standard deviations away from the mean. Okay, so what are two standard deviations away from this mean? Exactly, we need to add on another 4. And what will two standard deviations below the mean be? 16.6, perfect. And then finally we're going to look at 3 standard deviations away from the mean. So what are 3 standard deviations above the mean? Exactly, add another 4, perfect, 36.6. 3 standard deviations below the mean, 12.6, perfect. Now what we're going to do, or what you would get the kids to do, but I won't get you to do it, is we're going to get them to count from the table above how many numbers are between 1 standard deviation below and 1 standard deviation above the mean. So in other words, how many numbers are in between 20.6 and 28.6, and they have to count them. So we pretend we counted them. So there's my 20.6, there's my 28.6 is roughly there. So there's all the data that lies within 1 standard deviation of the mean. And that's what's special about the normal, just how much data lies that close to the mean. Okay. So when we count that, we have 144 out of the 200 are within one standard deviation. If we look then at two standard deviations, we're looking between the interval 16.6 and 32.6. And if we look at that and count those, that is 186 pieces of data within two standard deviations from the mean. And then finally, my 3 standard deviations from the mean. Okay, and we count these and we can see that that's mainly all of my data, 197 pieces of my data. Now, the kids are then asked, change these into percentages. So the numbers that we see here is 72% was within one standard deviation of the mean, 93%, and 98.5% was within 3 standard deviations of the mean. So what are we trying to get at here with the kids? Yeah, the empirical rule. Okay, so the empirical rule is, I guess, this is if you were to look at a massive population, not just the 200 foot lengths, but if you were to look at a population big enough, your numbers will work out as 68%, 95%, and 99.7% for 3 standard deviations away. So this is called the empirical rule, or sometimes the kids call it the 68, 95, 99.7 rule. And it's because of the predictability of the normal distribution and because of our knowledge of these numbers, we can use these to make little predictions for ourselves in our own work. Okay, so what we're going to do is we're going to have the chats by looking at some questions. Okay, so can you open up, excuse me, on page 10. Okay. So on page 10 we have a question. The mean height of a group is 166.6 and the standard deviation is 13.3. Based on an assumption that the distribution of heights is approximately normal, use the empirical rule for the following questions. Okay, so number 1. 68% of this school's students have heights between what and what? And this whole question is going to be based around the empirical rule and the percentages. But what I think is a nice thing to do is, sure, figure it out before you do the questions. Isn't that just easier? So what we'll do is, I think it would be good if the kids got into this habit of just in their rough work, or little rough normal distribution and figure out their percentages and their numbers, and then it make it so easy to work to the questions. So our mean was 166.6 and our standard deviation was 13.3. So here's my intervals worked out, and here are my numbers. Okay, so this will make it easier. So number 1, 68% of this school's students have heights between what and what? So what do you think?
153.3.
Yep, perfect.
0.9.
Perfect, exactly. So here are the heights that 68% is in between. Perfect. What percentage of students have heights between 140 and 193.2? Perfect, 95%. And the last one then, a school tour is being organised. All students can apply to go on it. There is a roller coaster at one location on the tour. You have to be over 140 centimetres to be allowed on the roller coaster. Okay, so you have to be over this. You have to be over 140 centimetres. So what percentage of students will not be tall enough to go on the roller coaster? So what can the teacher estimate if she's wondering, how many do I reckon won't be allowed on this roller coaster? Okay? So what percentage of the people she brings won't be allowed on? Perfect, 2.5. How did you get 2.5? Exactly, you're right. So 95%, if we take it away from 100, we're left with this little tail here and this little tail here. So that's 5%, isn't it? So we're only looking for half of that, and we can do that because it's symmetrical, isn't it? So half of that will be 2.5% won't be let go. Perfect. Okay, so this is a little question from the NCCA. Okay, and I'll let you just do this one yourself. So page 11, how will we go with that? So here's our little model of our numbers. So to enter a particular college course, candidates must complete an aptitude test. In 2010, the mean score was 490, so there's my mean score, with the standard deviation of 100, and that allowed me to get my intervals there. The distribution of the scores on the aptitude test is normally distributed. Okay, so number one, what percentage of candidates scored between 390 and 590? 68%. That's like the warm-up question. Okay, so number two, one student scored 795. So how does this student score compare to the rest of the scores? Yeah, he's top. He's top, what percentage did you say? Top 0.15. So he's just, or she is, either. It's just amazing. Yeah, they're way up here, aren't they? They're way, way above average. Okay, in the top 0.15. Excellent. And then number three, the college admits only students who were among the highest 16%. Okay, so what score do you need to get above to be in the top 16%? 590, perfect. How did you get the 590?
The 1 minus 68 divided by 2.
Perfect, so 68%. Take it away from the 100 will be 32% for both these sides, and then you divide it by 2, so here is 16%. So you got your 590. Perfect. Anybody do it any other way? No? Perfect. Okay. So we had that, and just as an alternative, just in case, you can also look at, from 490 backwards, you can treat as 50%, can't you? Okay, and then half of this then will be this part here. So that will be our 34, and our 50 is 84, so that leaves our 16 there. So there's lots of different ways of looking at it. Okay, so then finally we know our honours leaving cert students. They need to take it a step further, don't they? They need to be able to look at a standardised normal distribution. And that's for probability purposes, isn't it? Okay. So this is in their log tables where their distribution was standardized so that what is the area underneath that curve if we're going to use it for probability? Yeah, 1. Perfect. So we have a standardized normal distribution with the area underneath is 1, and what we do is we get what they're called our z-scores, isn't that right? And a z-score just tells me how unusual a piece of data is. So if I have a z-score of 1, I know that I'm just 1 standard deviation away from the mean. If I have a z-score of 1.5, I know that I'm 1.5 times away from the mean, etc. And we can use those z-scores and the tables to find probabilities of getting certain pieces of data. Okay. We're not going to go into it too much. If you're looking for extra information on that, there's loads of lovely slides to practice with your honours leaving certs under the modular course from the first year of Project Maths on the Road. Okay, so this is the website. Under modular courses, if you click into strand 1, you'll see there was a modular course all on probability and statistics, and lots of probability, very good. And look, course notes, click here, you'll get your PowerPoints, your course notes, everything there to download for yourself. So you don't need to do your own PowerPoints for all your probability, they're all there. Okay. So I've got another wee question for you now. This is mobile phones. We're back to our census at school here. Right. You wanted to work out which mobile phone company is the most popular among Irish second level students. You used a sample of 100 students and you found that Meteor topped the survey with 42%. Okay, so 100 students, you surveyed them, Meteor tops the poll at 42%. What percentage of all second level students in the country use Meteor? It's a tough one, isn't it? Yeah, exactly what you're saying. You want to say 42%, but you're nearly afraid to commit to it. And is there a reason why you might be afraid to commit to the 42%? Exactly, it's only a sample of 100. Now, do you remember this morning when we did our dot plots? Now, what if this lady took a sample of 100? Is her sample going to look the exact same as yours? No, you'll have sample variation. So a sample is a very good indicator. But I guess if you're going to, we call it infer. If you're going to infer to a population from your sample, you have to be careful that all you did was take a sample. So all we do is buffer it with the language. So instead of saying it is 42%, what might we say? Nationally, in general, it's around 42%. You know, you just have to be careful with your language when you're inferring. So around 42% nationally, looking at my survey. Okay. So interpreting the results, this is where we're at now. We're trying to find out from our results what it tells us about our question. So we're down to the end of our roadmap now at this stage of the game. So this is, you'll see at the end of the roadmap, it says, it talks about inferential statistics, inferring from a small population to a small sample to a population. And the very first thing it says, no deterministic statements. That's just the fancy word for don't say it is 42%. And that's important for the kids. Because if they don't write down things like in general or tends to when they're making interpretations from a sample, I know it's not about exams, but they might lose marks, okay? Because that's important that they use the correct language. Okay. And we have to talk now about margin of error. That's what we're going to go on to now. So the thing is, it's all about your statistics. You want to have confidence in your statistics, isn't that right? So let's have a look at these statements. The first one, a polling company said it's 100% confident that a candidate has between 0 and 100% of the vote. Big deal, absolutely. Doesn't tell us a whole lot. Very confident, but doesn't tell us anything. A polling company said it was 50% certain that a candidate has between 30 and 35% of the vote. Is that a better statistic? Have you any problems with it? Yeah? Well, yeah, it's only half and half. It's only 50-50. They couldn't come on RT News and say, well, we're 50-50 certain that so-and-so will get 35% of the vote. Okay, so 50-50 is not too good. Or they could come on RT News and go, a polling company said it was 99.9% certain that a candidate has between 4 and 94% of the vote. Do you see that there's an issue with the balance here? It's like, where do you cut off your confidence with actually telling me something that's remotely interesting? So there's a balance to be played there. And not only is there a balance, it kind of depends what are you surveying as well. I mean, what level of confidence do you want on your shampoo bottle that says, you know, that this shampoo makes 94% of women have amazing hair? What confidence level do you want in that statement? So now what that means is we don't need to worry about the level of confidence, but what we do need to worry about is the margin of error and the sample size. Okay? Because the sample size is going to tell me a lot about how confident I am in my statistics, isn't it? Okay. So that's where the margin of error comes in. Okay? So the margin of error tells me what type of error to expect with a sample. Okay, so it's 1 over root n on our syllabus for the margin of error. So if we look at these, my mobile phones were a sample of 100, wasn't it? So if you sample 100, 1 over the square root of 100 tells me that there's a potential error of plus or minus 10% on your statistics if you use a sample of 100. What you often see them use on TV, the chaps on RT and the ladies on RT, they'll often go in and around the 1000 mark, because that gives you a margin of error of 3% either side, which is quite good. Okay. If you want very, very accurate 1% margin of error, you have to survey 10,000 people. Okay, and I guess that's not always possible. So 3% you'll see happening quite a bit. Okay.
So most of those Red Sea polls around 1,000, yeah?
Yeah, well, yeah, I've noticed that in the papers. They're usually in and around 1,000. Now, we've no idea how they're taking them. Are they doing the quota sampling? Or are they actually bothering to have any representation in their sample? We never hear about that side, sure we don't. So that's the nice thing about statistics. It makes you very consumer aware, you know, about your statistics. You take certain ones with a pinch of salt when you don't know the full story. Okay. So we talked about that then. So this is talking about consumer aware. This is lovely now. Again, for some reason, this isn't playing on my hyperlink too well. So I'll just go straight for this. Okay. Can we get the lights then, again, if you don't mind? Thanks very much. So I just want you to watch. Oh, sorry, that's the. Perfect. So I just want you to watch this carefully now. 75% of 52 women. Amazing. 75% of 52 women. Now, you didn't realize you were getting duped like that, sure you didn't. I mean, that's unreal, isn't it? I mean, it's such a poor statistic. The sample size is just way too small. And what's interesting, you could get the kids to go home now and start sussing out from the TV adverts or magazine adverts what is, you know, plausible and what's not. Because since I've seen this, I'm a little more consumer aware. And you will notice when you look at telly, even just staying with makeups for the minute, some makeups you will see a sample of 2,000 women come up at the bottom, and it'll be something like, you know, 82% or 91% of 2,000 women. And then you see other ones and they're like that. So keep an eye out for it. Okay. So again, I just got that on YouTube. You get all of that kind of stuff on YouTube, no problem. Okay. So another thing then that the kids have to do is, this is now up at Leaving Cert level, is something called hypothesis testing. And it can sound a bit hard, but it's not too hard. What it is a claim is made about a population. Okay, so a population, all the people in Ireland are all lovely women or whatever. A claim is made about a population. And this claim is called the null hypothesis. So the null hypothesis is denoted by H with a little 0, and it's a statement about a population. And what we're going to do is we always assume the statement to be true and try to prove otherwise. So you, like in a court of law, you assume it to be true and it's up to us to prove that it's not. So let's look at a claim here. Let's say it's about a drug and a company writes in a magazine, the new drug relieves migraine 70% of the time. So we'll assume it's true, but we will investigate it. So we might run a little sample ourselves. So a magazine or someone might go, well, you know what, I'm going to test your claim. So a newspaper investigates the claim by getting migraine sufferers to try the new drug. They get 100 results that say it relieves migraine 62% of the time. Now the thing is here, we don't really know, is 62% good or is it not? Is it close or is it not? So that's where your hypothesis testing comes in. We check what is the margin of error on 100, a sample of 100. So we know the margin of error will be plus or minus 10%. So we make an interval of 10% around our statistic. Can you see that? And what we want to know is, well, is the 70 in there? Because if it is, that's fair enough. And if it's not, we can say that we proved you wrong. So the 70 that is there, and what we have done is, we haven't proven them right, but what we have done is we've failed to reject the claim. Okay, so we failed to reject that claim. Okay, we'll just look at one more. We can go to our census at school here. Out of 200 students, census at school told us 34 are 100 centimetres or taller. Is this sufficient evidence to reject the teacher's claim at 5% level of significance? So what is the 5% tied in with? The 95%. And it's tied in to your formula for margin of error. It's there, okay? They don't have to worry about that. It's inbuilt in. So one problem here, though, is I'm talking about 34 out of 200, and here I'm talking about percentages. So we'll have to compare like with like. So first thing is 200, we'll see what our margin of error is, plus or minus 7%. We'll change our 34 over 200 into a percentage so that we can compare like with like. So 17% is what my census at school told me. And I have an error, potential error of plus or minus 7% on that. Okay, so let's look at this interval in relation to the population. 30%, does it fall in there? No, it's outside the boundary. So now we can reject the claim. We can reject the claim.